So we have these noisy rewards and a potentially complex mean reward function. The consequence is we might get really slow learning. So one solution, one approach is to have a low-dimensional linear reward model. We actually do a little bit more than this. We actually only model what's called advantage, a part of the reward model in a low-dimensional way. And essentially what's happening is you're trading learning speed with bias. And you might get better results because you trade learning speed with bias. Because if you learn too slow, you're going to definitely get bad results even if you have no bias.
Was there a window for the treatment effect? A fixed window?
So the reward is the 30-minute step count after that time point. So that's the window. That duration comes directly out of domain science. I mean, I could give you a whole series of talks on how you use domain science to constrain this experimentation strategy. It just comes completely, as you can imagine, all of this is informed.
So it's a 2.5 hour, that's a total 1 day.
Yeah, so there's 5 times a day, and they're about 2.5 hours apart. I mean, that's rough because they're related to your work schedule. And each time you look at the 30-minute step count after that time.
But their position is different based on the user preference.
Based on the user's work schedule and when they did it. Yeah, every person is different. This algorithm is going to run on each person separately. So, we're still trying to deal with these noisy rewards. So what we're going to do is use an informative prior. And it's one reason why we went with this Bayesian approach, is because now we can use information from prior studies in a really principled way. So our prior comes directly from the analysis of that 42-day study. The means come from the coefficients that we estimated from the population mean, the estimates of the population means from the prior study. The variances come from the prior study. The Gaussian, of course, is a computational convenience. We also have a week baseline. Every user that's in this study goes through a week where they're just randomized with constant probability so that we can update their reward function, their mean reward function, have a better estimate before we start trying to experiment and discover which action is best. So the other challenge, I mentioned this like multiple times, is how to ensure ability to conduct causal inference after the banded study. This is an incredible constraint. A lot of my CS colleagues, they would like to do something called the UCB algorithm. You can't, UCB algorithm, you're not going to be it uses internal variability to experiment. That's not going to help you in any causal inference. You can't do causal inference afterwards. A lot of people would like to do some sort of complicated earn randomization with maybe explore then exploit kind of strategies. Again, you're dead. You can't do any kind of causal inference afterwards. Or you could, but you'd have to make gross assumptions that might be untenable. So this also motivates us to use posterior sampling, because our posterior probabilities are randomization probabilities. As a statistician, I look at these posterior probabilities, that's all I think about. I'm randomizing. And we also, what we do is we ensure that these posterior probabilities, if they go below in this study, it's below 0.1 or above 0.8, we clip them at 0.8 and 0.1. 0.8 is a default probability, and that's the probability we want to use if there's no current evidence of an effect. 0.8 is an upper bound, and it's determined by Berger. Both 0.1 and 0.8 come directly out of the domain again. So now back to the whole delayed effects and the fact that we foolishly have a horizon h=1 algorithm, and we have these delayed effects. So the big concern here is that you may end up over-treating, because at least in the near time, it looks like it's a great idea to send lots of messages. So how might you deal with this? But the concern, so the natural thing is to say, okay, I'm going to do a full RL algorithm, Markov decision process. But the problem is the target, when you use a full RL algorithm, is the immediate reward plus a prediction of the future sum of rewards over that horizon. And that target, if you add that prediction can be very, very noisy. And that reduces the learning rate. So there has to be this bias variance trade-off. Right now, with a bandit, I just use the immediate reward and I put a 0 in for the future prediction. Very low variance, but possibly highly misleading, right? So we want searches for what's a low variance prediction of the future rewards that might accrue if you take this action right now.
Question. So did you, I've lost track, did you say that there's just a binary decision to treat or not to treat, or are there levels?
Actually, it's much problem, yeah. Okay. Yeah, but here, the only thing we're going to learn is the binary decision. And the reason why, I'm a statistician, right? We know if you work in clinical trials as a statistician, if you want big signal, you want very discordant actions. And the most discordant actions, or most different actions in this setting, are don't bother the person versus send something. Now, there's a whole variety of sends that we're very interested in, and that we do a lot of analyses to learn which type of message to send. But that's, I'm not talking about that here. The signal, the best place to place my bet, the place I'm going to put bets on is send or not send. So instead of selecting my treatment based on the posterior probability that the reward under action 1 is minus the reward under action 0 is positive, I'm going to add a little term to that. That's this eta in kind of purpley blue. And this eta should be a low variance signal of the delayed effect of sending an action versus not sending anything at that time. That's what it should be. So what do we do? So what we do is we form a low-dimensional proxy Markov decision process in which the dose, that is, the dose, it's how many times you've received a message over the past 7 days. It's exponentially discounted. So it's not over the past 7 days, it's exponentially discounted in the past. Over which the dose evolves deterministically. All other states are just sampled. So at each time, we update the empirical distribution of the states for that individual, that user. We update the reward function, so what we update is this reward function, is that we get the posterior distribution of this reward function, and then we average out all the states except for dose, using that empirical average. Then we do standard Bellman iterations to solve for the value function. And the value function in this context is our prediction of the sum of rewards over the subsequent time. We actually use a discounted horizon to do this, and the discount rate is a tuning parameter in the algorithm. We tune the discount rate with prior data.
So if we worry about this accumulate, like too many messages cause burden, then what will be the difference if you add the eta in this posterior function, and also if you add some like penalty on the reward?
Right.
Will it cause difference?
Yeah, so the first algorithm we worked on was one where we were using a PID controller on top of the bandit, where we put a penalty on choosing an action. But it was so hard to tune, it's so sensitive. The great thing about this algorithm is it's very stable. And it's not causing trouble, and sometimes it helps. Yeah. Whereas the PID controller was just so hard to tune. We just had enormous trouble tuning it. But it was a direct penalty on sending an action. Let me show you how we use this prediction of future rewards. So the prediction of future rewards here, we take its expectation given the current dose, prior dose under action equal 1 versus given current dose action equals 0. We take the difference. We tune a discount rate For it, the data indicated it should be a 0.9, so that's what we're using right now in the study. It's not being updated during the study. It's just 0.9. And this difference here will be negative if there's evidence of too much treatment. So if this is negative, then the posterior probability of this whole sum being greater than 0 is lower. That's the whole idea here. It's very much a poor man's effort to anticipate the future. So so we used the first part steps to form a generative model, and then we used threefold cross-validation, this is each subject. There were 37 subjects in the first study, so there's 37 columns. And we looked at how much would their overall step count improve if we used this little proxy of the delay impact. And it looks great, man. I mean, it looks great. Like most of them would get a big improvement over the study. So we were really excited. So now I'm going to show you some results. So this was August 8th. So here's one of our users. So this study, we didn't register it. Because we didn't register it, things weren't locked down. We won't ever be able to publish it in a top-notch clinical trials journal. I mean, we won't be able to go to a top-notch medical journal because it wasn't pre-registered, because the focus was on the development of the algorithm. But the next study will be registered, and I won't be able to do what I'm doing, showing you results like this. I won't even be able to look at the data. So here's a user. Here's the posterior mean on the y-axis, and then here's the dates. So you can see this is the summer ending in 8/6. I don't go past this because we changed the algorithm a lot, and so things look different. So what happened was the user comes in, and this guy is really, this is a really big effect. I mean, this guy's very engaged. Really walks a lot when he gets a message. Doesn't walk very much when he doesn't, or he or she. I don't know the gender. But and then with time, things start to deteriorate. But the person is still pretty engaged. Notice we're above 0. The posterior mean of the treatment effect. So this is a contrast between getting the message versus not getting the message. It's always positive, but it still does best. So what's happening to the randomization probabilities when you see this? Because this is like an estimate of that individual's treatment effect, right? Sending a message versus not. So now I'm going to show you the randomization probabilities. So the black one is the one that's actually being used in the study. This is the one, wherever that black circle is. So what you see is early in the study, the individual is not being randomized with around 1/2, and then they're so responsive. Remember, there was that big peak where that individual became very responsive. So then the probabilities go up and they hit that upper limit. I mean, essentially, Thompson sampling wants to go to 1. It wants to exploit. Good thing we didn't allow it to do that, because then the individual starts to decrease in responsivity, and the probabilities now start to trail down to back off and not send the intervention as much. There's a lot of problems with this, I'll just mention. So the red, we wanted to see what would happen if there was no proxy. The proxy is that little prediction of future delayed rewards. So I'm going to talk to you about the problems, some of the problems. So the first, there were multiple issues. The first thing is, if you look at this graph, it's pretty clear the user starts to reduce that individual. And this is a typical user. The responsivity starts to decrease, maybe 7-10, or it's starting to come down, but the probabilities, they don't come down until around 7/16 or something. So there's this delayed tracking and we would like to have a little bit more faster responsivity to that, maybe more anticipatory if we can. Another issue as well is that it didn't, like if you look at this graph, it looks like there was no real, okay, so the black, these are the randomization, the black dots are the randomization probabilities that that individual truly was experiencing. And you look at if we hadn't have used that forecast of the future, that prediction of the future, they're a little higher, but they don't look that much higher. It turns out that that's all relative to the probability itself. So actually there's more difference here than you see. But we thought the proxy would really reduce the probabilities a lot. It didn't reduce it to the extent we would like to see it. Okay, I just want to talk about some open questions. So the trial, like I said, I actually have more graphs, but they're different issues because we changed the trial in a number of ways. I can talk about that. So some of the things we're struggling with is how do you design a trial in which you're personalizing? Because that's what we're talking about here. This is precision medicine. This is an attempt to do precision medicine, right? How do you design a clinical trial like that? Here, one idea might be you want to maximize the total reward over your horizon, subject to lower bounds on power to detect particular causal effects. You can't just try and maximize the rewards. That's not going to work because you have to do causal inference afterwards. So how do you constrain your utility, the criterion, so that you can do those analyses, those causal inference analyses? What we did was we took a poor man's view. We aimed to maximize the total reward subject to bounds on the action selection probabilities, but that's clearly not the best approach. So how do we do this in the future? How do we design personalization trials? That's not clear this time. Also, any kind of learning algorithm one uses, you use a whole bunch of assumptions for that algorithm, and I gave you a bunch, like I used Gaussian errors, I had a Gaussian prior. None of that should constrain the kinds of analyses you want to do. So there's design of the learning algorithm, assumptions you put to design a learning algorithm, and then there's the assumptions you might want to use when you analyze the study. The assumptions you use when you design the the RL algorithm should not somehow constrain your analyses afterwards. You separate the algorithmic assumptions from the environment, what's happening in the real environment. You separate it and you want guarantees with that separation. So this is a question right now we're really struggling with. It turns out in this study right now, there's 5 intervention components that are being. One is having that algorithm that's spreading out the anti-sedentary messages. The other one is this activity suggestion, the RL algorithm. And then there's each one, they're all at different time scales. One is every 5 minutes a day, we look to see if you're sedentary and we randomize. This one was every 5 times a day. We have another one that's every day in the morning. And then we have another one which is weekly. How do you have all these different components and you personalize all of them and you make them collaborate? Because if you bother someone too much with one, they may not respond to another. So and in addition, all of these studies have some distal outcome that you want to optimize. How do you induce collaboration among these different agents in some sense, RL algorithms, so that you get collaboration so that that distal outcome is being achieved? I mean, this is a critical thing. Every single trial we're involved in a number of these trials, has this problem. And right now we just ignore it. We just completely ignore it. This is my last slide. So I just want to say, what's the long-term goal? Where are we marching in a very stepwise fashion towards? What we're our long-term goal is that when someone releases an app like Kaiser or another health maintenance organization or the VA, is they'll have all these treatment components. That'll be part of the app. And then they'll have the learning algorithms too. And they'll be part of the app. And then there'll be a monitoring algorithm as well that monitors that. That's our goal. how do we achieve that? And that will go, so that it can actually be used in real life. And in that entire process, there's always going to be a bias variance trade-off. That is pervasive throughout the entire problem, the trading bias. Okay, so I just wanted to recognize all my collaborators. This is just a subset of collaborators, and they're not all involved with this study, but these types of studies take a lot of people, human-computer interaction, scientists, behavioral scientists, sensor guys that work with sensors, statisticians, all kind, app developers, which are normally computer science master's students. All of us have to work together to run a study like this. Thanks.
So, I'm just trying to understand what question about the optimality here would be. So, say I'm doing causal inference, so I have I use Nancy as those function estimators. So there's a variance, and one variance is small. And sometimes, like the microphone does this, he says, oh, I have randomized study, so my propensity score is correctly specified. So
Right.
I drop
It's
myself
not.
to screwing up the other model versus the variance as much as I can. So is this like, you're controlling the propensity score here?
Right.
So you have some complicated, let's say, response model that exists because people respond.
Yeah.
So that's fixed. So is this like you're trying to mess around with the propensity model to reduce variance? Is that how I should think about it?
No, actually what happens is there's usually a bunch of secondary, when you register the trial, you have secondary outcomes that you're really interested in. They're not ones that you did any kind of exploitation with. And you want to be able to do inference for those secondary outcomes. So like a typical activity trial, you're going to also look at their diet, aspects of their diet, because there's going to be components that have to do with diet. You're going to have all kinds of issues like how are they managing their blood pressure? That might be it. So there's going to be other outcomes that you're really interested in, and you want to continue to be able to think about causal inference for those. So like, did these actions have any impact on these other outcomes? There will be different ways of measuring physical activity, like bouts per day, that you might be interested in. And you want to be able to, you might want to form a warm start policy for a future trial for a different reward, like bouts of physical activity.
So you want to be able to support causal inference on lots of targets, basically.
Yeah, you want to be able to, and normally though, in a clinical trial, you have to pre-register. So you pretty much have to choose your poison. So you have one target, which is the reward, and then you'll have like 2 other targets or something, and you'll have pre-specified analyses. So it's not like it's just, a big mining kind of exercise. It is pre-specified. So there is this hope that you could design the study to ensure you have enough power to detect, to do these other analyses. It's not like it's a non, it's something we could achieve if we can figure out how to do it.
So the impact on the causal inference, is this quantified? Can you express a budget or a trade-off of what the sampling algorithm does to the causal inference ability?
Yeah, so with this algorithm, it's individual. Each person has their own, the algorithm is working separately on each individual. And the causal inference analyses that occur after the study's over, they get their information across individuals. So a lot of the traditional biases we see, like with bandit algorithms and advertising, they don't occur. Now, that said, we're about ready to start. We're going to add some people to the study, and we're going to pool across people. There we have to deal with the biases that occur due to the selective sampling. And that's a big challenge. I mean, I have to say, this field is completely open. I mean, everywhere I look, I see a problem that we need to deal with. But how, because definitely it's clear we should do some sort of pooling in these studies. It's absolutely clear. If you want to learn faster, people are not, it's not like people are all pink. Some are pink and some are red. It's just not like that. People are variations, right? So there should be some gain to pool. But right now, if we pool, the causal inference analysis are just a disaster. So how do we do that? And certainly we're working on that. And the biases that occur because you're doing selective sampling are a big issue here. The other issue too is that in the literature, when you talk about this selective sampling with bandit algorithms, most of the time people are worried about over-sampling of the more, they assume they have a margin, that the arms are different, and they're worried about over-sampling the arm that's more important and under-sampling the other one, so you get biases. That's not where the real problem is in this world. It's when you have very low signal-to-noise ratio. Then you get really peculiar biases coming in. It's very interesting. Yeah.
So on kind of a related note, say I have this app and I happen to drive to work with a friend, and so now when I start parking 10 minutes further from work, my friend also parks 10 minutes further from work.
Yeah.
They happen to have the app too, but they aren't getting a ping at the time. So now I have interference effects.
Yeah, I think if we were doing a wellness study, that might be, in our setting, I guess your friend could also have hypertension and could also be at Kaiser. You understand, it's unlikely in our studies that people ever meet each other. We're not doing any group therapy. That would be a big issue for group therapy. So I don't see interference right now being a problem. Right, I don't see that being one of those problems that we have to deal with right now. Yeah.
So since the intervention is technically a binary,
Yeah, the way we're treating understanding, we're acting, it's
yeah, it's a
binary.
binary, then technically your action is yes or no.
Right.
Then calculate a predetermined outcome as a ratio of change or a percent of change for whatever baseline. Do a stratified, randomized sampling of people based on that calculation, and if all of them get the app, a group gets no messages at all, a group gets messages all the time, and a group get the RL. And then you can decipher the cause.
Yeah, once we've optimized, so we are playing the role of engineers. This is like a fraction. Our designs are all factorial designs, and the whole game is to get the RL algorithm solid enough and well run enough so that we can do comparison against some alternative, like you just mentioned. But this is an optimization trial. It's an optimization of a personalization. So, and if you go back to industrial statistics, we do all these big factorial designs. That's not to evaluate. They're optimization studies, and that's what this study is. We're trying to build an RL algorithm that will work really well. So when we go to that two-arm setting, we're going to get big effects, and we won't have to doctor the statistics at all.
But the algorithm seems to be based on rewarding the app, not rewarding the user.
Oh, yeah, we also, I didn't mention this, but we have a whole other studies where there's some of the actions are rewards for the user.
Okay.
So sometimes we want the user to do something that they don't find rewarding, and we have to find our actions are sets of rewards for the user. That's just another action space in the RL world. It's not.
Because this one is aiming to reward the app itself.
Well,
Through an
the meaning of
actuator.
reward here is to reward the algorithm. But when we talk about rewards for the user, we'll use the word reinforcers. And so, for example, if you answer a question, we might ask you, which is very burdensome, you might get a little meme or an inspirational quote as a reward. When should we give you this? Let's not give it to you too much because it won't be exciting anymore. We have gamified interfaces on a lot of our apps. I mean, I'm totally into rewarding the user because it's hard to change.
Well, we do the same because those who are going to be ready to work right now are going to be rewarded with some food. I don't know if it's not counterproductive.
No, I think we should all walk to where the food is and get rewarded.
We have very nice food at Drink Seeds as a refreshments in White Hat 301. Okay, so let's stand up.